Okay, what we've got here is the vector equation of a plane. So we've got r is equal to position vector of a point that's actually on the plane plus some scalar multiple of a parallel vector here, parallel to the plane, plus a scalar multiple of another vector that's parallel to the plane, but these two vectors are not parallel. So that's our vector equation of a plane in standard form. Now to convert this vector equation into our Cartesian equation of a plane, what we can do is separate out the I, j and k components, and we can say that x is equal to 2 take lambda plus 3 mu, so they're the I components here, and then y is equal to 1 plus 2 lambda take mu, z is equal to 3, there's no lambda value here, plus mu. So there's our three equations there. And what we've introduced here is x, y, and z so that we can get the Cartesian equation of the plane. So all we need to do is eliminate the lambda and the mu from these three simultaneous equations, and we'll have that Cartesian equation of the plane. Now we could do that by hand, looking at equation 1 and equation 2, perhaps eliminating lambda. Then equation 3 here, lambda's already eliminated, so once we'd eliminated lambda from these two equations, we could then eliminate the mu from the remaining two equations to get an equation in terms of x, y, and z only. However, this is very easily done on the class pad. So what we can do is just put these three equations into the class pad, like so. And the little trick here is, I guess the problem is that we've got 5 unknowns, x, y, z, lambda, and mu. But what we can do is if we solve for x, lambda, and mu, so let's just pop that in, x, comma, lambda, comma, mu. What we'll end up here is with x in terms of y and z, lambda in terms of y and z, and mu in terms of y and z. And the first equation, when we solve, which is this first one here, you can see we've got x in terms of y and z only, and that's our Cartesian equation of a plane. So let's write that down. We end up here with x is equal to negative a half y plus 5 on 2 z, take 5. Just some simple rearranging here, multiplying 3 by 2 and some rearranging, we get x, 2x plus y, take 5z equals negative 10. And there's our vector equation of, our Cartesian equation of a plane. Now obviously if we wanted to convert this Cartesian equation now into a vector equation in normal form, that's very easy. We just write that as vector r, scalar product with, we use the coefficients of the x, y, and z terms, 2, 1, negative 5, and set that equal to negative 10. So you can see here we've gone from vector equation of in standard form to Cartesian equation, and then finally down here we've gone to our vector equation in scalar product form, or normal form if you like, by taking coefficients of the x, y, z values, making that into this normal vector, and the negative 10 comes out over here.